Log on, tune in, find out. Another good idea from Cambridge.
Okay, so I'll speak about the Floquet spectrum of a quantum graph. And let's see. Yeah, so, well, yeah, we'll start with the setup and define what I mean by Floquet spectrum and quantum graph. So, yeah, quantum graph, we've heard a few times what this is. And then for the rest of the setup, I'll mostly adhere to a paper from Gavot and Okada to define my operators. So first we'll start with a one form on each edge. We can just define as being a one form on a quantum graph just as being a one form on each of the edges. And I think I am missing an inch back here. That's very sad, but okay. Okay. Can you just... that seems... Yeah. Ooh. That's a little bit too much, but I'm still seems to be wider than everything. No, that doesn't do anything. Okay. Well, I'll hopefully say all the important things, and then you have to do some guesswork to see whatever is missing here. Okay, so yeah, so we define one forms on a quantum graph just to be a one form on each of the edges. And once we have one forms, we can just define the sort of standard D operator, and then we'll modify it by just adding in a one form. So going from functions to one forms, just take D on each edge, and then add a one form. And then when we have that, we can define some kind of Schrödinger type operator by taking this operator D and multiplying it with this adjoint. We just get the adjoint by taking an Hermitian inner product on each of the edges and just adding them all together. That gives us an inner product on the whole space, so we can define what D star means, and so that gives us the Schrödinger type operator. And in the simple case of alpha equals 0, that's just the standard Laplacian on the graph. Yeah, so then quick check that one can do is if I have two different one forms that just differ by an exact form, then nabla alpha and nabla beta actually have the same spectrum, and that's sort of a fairly quick check. You can just directly transform the eigenfunctions. If I have an eigenfunction for one of them, then I can get the eigenfunction for the other one and multiply by e to the I phi, ic. And so what I'm going to do is I'm going to look at the spectrum of all these operators nabla alpha that I defined here.
So not only look at the spectrum of the Laplace operator for one of these operators, but I'll take all of them. And so now I've given myself a whole lot of information about my graph. See what I can do with my lot of information. And so the key tool to get any useful information about all of these things is just to use one of these exact trace formulas that are about there for graphs. There's various versions of exact trace formulas that several people in this room have shown. The one that I've cited here is by Kodish and Simlansky. In some sense, it doesn't matter, at least for the things that I do, which one you take, because they all give you the same kind of information. We start off with a sum over all the eigenvalues, which here we have a Dirac delta distribution for each one. Then we have one term that gives us the total length of the graph, one term that gives us sort of the Euler characteristic of the graph, or chromatic number, as Greg Berkeleiko called it. And then we have a term that is an infinite sum over all the periodic orbits in the graph, and for each of these periodic orbits, we get some kind of complicated coefficient and then some exponential. And so that's what we're sort of trying to use and get information out of. And sort of this is, in some sense, the point where you can see where this additional power of having the collection of all these spectra comes in. Because if my graph is sort of not generic, then I can have lots and lots of periodic orbits that all have the same length, that will all give me exactly the same coefficient. And that's sort of the reason why in a lot of these papers about these things, people assume some genericity assumptions about their graph.
that are just going in directly here, which means that all the periodic orbits have different lengths. And that's sort of, I do not assume this case here, and because I have lots of spectra, I can sort of get around these genericity assumptions. Because the hope is that sort of if I have this for each of, for lots of different alphas, then sort of for at least some of them, I will not have any nasty cancellation. With enough information, I can sort of still get information about each individual periodic out of this formula. Okay, so for each single periodic orbit, for each homology class of periodic orbits in my graph, there's one representative that's sort of the shortest in length. Possibly there could be several, but sort of we'll call the one that's shortest minimal. And then the first thing that it can show is that I can get the length of all the minimal periodic orbits of my graph. And you can, in some sense, sort of already see the weaknesses of this theorem. Because in order to get anything useful, I need a graph that actually has a whole bunch of cycles so that I have some homology. If my graph happens to be a tree, then this sort of tells me, well, I can get the length of a single point because it would be the only orbit that's not contractible. So that's all this business is sort of only interesting if you have graphs that actually sort of do not look like trees but have lots of homology floating around. And so a slightly different version to just reformulate sort of the same result. One can define an Albanese torus of a quantum graph. This is again KS, but two different people. This is Kotani Sunada, that are, I think, also both here. And sort of I can sort of use my information about the homology to just get the Albanese torus of a quantum graph. And yeah, sure. That already seems like quite a nice gadget of information, but sort of just to draw a very simple example that this does not give you the entire graph. Well, you can first do the stupid thing and sort of just attach trees, but even if you don't do that, you can have graphs that say look something like this. And then if I look at my Albanese torus, it will only give me information that involves both of these edges at once. So I can get sort of like the sum of the lengths of both of these edges, but the Albanese torus won't tell me anything about how long each of these edges are individually. Sorry?
What kind of structure you put on the Albanese torus?
So with the that's just a real torus. So just from the homology and of the inner product that comes from the homology.
Okay, so you
and then so this it's a real torus. And yeah, so then another thing that you can think about is sort of trying to figure out whether a graph is planar or not. And there's sort of a very old theorem that tells you when graphs are planar, which is just saying when the cycle space has a simple basis, which means that I can sort of generate all the cycles in the graph by just using every single edge at most twice. So if we look at this example again, then I can have one cycle here, one cycle going around here, and one cycle here, and then I haven't used any edge more than twice. And this graph is clearly planar. And so you can try by hand if you draw, say, like K5, which is the smallest example of a graph that's not planar, then you can't find such a simple basis. So this theorem seems sort of somewhat related to the kind of information we have, and we can use this, in fact, to determine, in general, from the Floquet spectrum of whether a graph is planar or not. And so there's, in that sense, two key steps to doing that. Well, the first thing is that this thing talks about the cycle space, and what we're looking at is homology. So you need to first do some kind of translation there, and then once we've done that, we sort of somehow need to look at various generators of the homology and try to figure out whether three of them share an edge or whether there's sort of only pairs of them share edges. And this is sort of already interesting in the sense that if I just look at the spectrum of a single operator, so say the standard Laplacian, then there are examples of quantum graphs where a planar quantum graph is isospectral to a non-planar quantum graph. So that can happen for the spectrum of a single operator, but sort of as I showed here, if I have the spectrum of all these operators, then this cannot happen anymore. And the last thing we talked a few things about is the dual graph. So if I happen to have a graph that is planar and I found some kind of embedding, then I can just dualize it by sort of replacing all my faces by vertices, including the outside, and all my vertices by faces, and so I just sort of start drawing connections here whenever there's an edge in between them, so I'll not draw the complete thing. And then I just get sort of started from my graph some dual graph. And sort of using this idea of dual graphs, I can see that I can use all the information about the homologies that you have to construct a dual graph of a given planar graph. But there's already a small problem here because it says embedding of a graph, and if your graph is more complicated than the simple example that I drew here, there can be several dual graphs of the same graph that don't need to be isomorphic. And then when I sort of dualize again, then it's not guaranteed that I actually get the individual graph back that I started out with, but I get something that's sort of what's called too isomorphic to the graph. So I don't get the full graph back, but I get something that's sort of, well, it's looks like my graph is with something.
And if my graph is 3 connected, then that's
I'll get the combinatorial graph that's underlying my quantum graph back out of the graph. And there's sort of the second part of it. If I know that I have my graph looks like this, say, then I want to still find all the individual edge lengths out of this, and that's sort of what this theorem talks about. If I'm given any sort of combinatorial graph and see this is my quantum graph and this is its Floquet spectrum, then I can use all this information to identify what all the individual edge lengths are. And I think I'll not talk about how to do that, but just keep time for 1 or 2 short questions. Thank you. That's the list of references that I cited all over my talk.
Other questions? Yes, please.
Actually, can you make similar statements for in the discrete case?
I
mean, to find sort of one forms, can you then similarly and then
yeah,
family
it
of
seems like
spectra?
an interesting thing to try, but I haven't tried yet. But I would assume that if you get a reasonable definition of a one form that gives you something interesting, then presumably you can do similar things.
At least the formulation.
Yeah.
I don't know the proof.
Yeah.
And your operation coincides with the Pratt operation, the kind of sections of the Pratt band associated with the one form alpha.
Wow.
Or kind of the twisted.
Yeah. Oh. I think so, but I would have to carefully check the details.
Okay.
I don't know.
There are no more questions, so thank you very much.